Before we enter the world of formal definitions and policies, let us first understand maintenance as it is lived and felt on the factory floor. Consider the old experienced loom operator in a Varanasi textile mill. For 40 years, he has worked with the same set of power looms. He doesn't need a sensor to tell him something is wrong. He can tell by the subtle change in the rhythm of the shuttle, the slight tremor in the frame, or the faint, high-pitched whine from a motor, that a problem is developing. When he stops the loom to tighten a loose belt or oil a dry bearing before it breaks, he is practicing the most advanced form of care, reactive approach, jugaad until it breaks. This is the equivalent of ignoring the sputtering engine of a delivery van, patching up leaks with tape, and only calling the mechanic when the vehicle refuses to start, leaving a full load of goods stranded. Time-based proactive approach, the ritual of care. Think of the ancestral home that is whitewashed and repaired every year before the monsoon. The family doesn't wait for the roof to leak or the walls to crumble. They perform this ritual based on the calendar, knowing that timely upkeep prevents greater damage later. Condition-based proactive approach, listening to the whispers. This is the master craftsman listening to the kir-kir sound of a bearing, or the plant engineer noticing a motor is running a few degrees hotter than usual. It is the act of using one's senses, augmented by modern tools, to diagnose a problem in its infancy. Maintenance is formally defined as the aggregate of all technical, administrative, and managerial actions performed during the life cycle of an asset, intended to retain it in, or restore it to, a state in which it can perform its required function. The primary objective transcends mere corrective action. It is a strategic function. It is crucial to distinguish between maintenance and repair. Repair constitutes a purely reactive activity undertaken to correct a fault that has already manifested. In contrast, maintenance encompasses proactive and planned activities designed to prevent failures from occurring. An effective maintenance strategy seeks to maximize useful operational life while minimizing total cost of ownership. In contemporary industrial environments, maintenance has transitioned from being perceived as a non-value-adding expenditure to a critical contributor to competitive advantage. Overall equipment effectiveness, OEE, is a composite measure of an asset's availability, performance, and quality. OEE equals availability times performance times quality. A robust maintenance program directly enhances availability by minimizing unplanned downtime, improves performance by ensuring equipment operates at designed speed. Although maintenance activities incur direct costs, they represent a strategic investment to prevent substantially larger costs associated with unplanned failures. These failure costs include not only direct repair expenses, but also significant indirect costs of lost production, idle labor, and premium charges for emergency interventions. The hidden costs of downtime can be devastating to profitability. Improperly maintained equipment is a significant source of process variability, which can directly lead to product defects and quality degradation. A systematic maintenance policy is indispensable for ensuring a safe working environment and adhering to environmental regulations. The failure of critical assets can precipitate serious industrial accidents with significant legal and financial liabilities. Breakdown maintenance is a run-to-failure methodology. No maintenance action is performed until the asset has ceased to function. This policy is economically viable exclusively for non-critical, low-cost assets where the administrative cost of proactive replacement exceeds the inconvenience of failure. However, this approach has high unpredictability, substantial failure costs, and complete unsuitability for critical operational equipment. Preventive maintenance involves executing maintenance tasks at predetermined intervals to mitigate the probability of age-related or usage-related failures. These intervals can be time-based, such as every 6 months, or usage-based, such as every 10,000 kilometers. This policy is most effective for assets whose failure probability increases with time or use, following the classic bathtub curve of failure rates. The bathtub curve shows how failure rates change over an asset's life cycle: high initially, low during useful life, then increasing in the wear-out phase. Predictive maintenance involves real-time monitoring of an asset's operational condition to predict the incipient stages of failure. This data-driven approach is a cornerstone of Industry 4.0, aiming to maximize the PF interval, the time between discovering a potential failure and its decay into functional failure. Common techniques include vibration analysis for rotating equipment, infrared thermography for electrical connections, and oil analysis for internal machinery health. When sensors detect a progressively increasing imbalance, data analysis can predict bearing failure within a specific time frame, enabling scheduled replacement. Reliability-centered maintenance is not a singular maintenance type, but a holistic engineering methodology to determine the most effective maintenance strategy. RCM involves rigorous analysis addressing 7 key questions. What are the asset's functions? How can it fail? What causes each failure? What happens when failure occurs? RCM is predominantly used for highly critical systems in aviation, nuclear power, and defense industries, where failure consequences are severe. The output is a fully documented, optimized mix of maintenance policies strategically applied to different components and failure modes. A frequent quantitative analysis in maintenance involves the decision between individual item replacement upon failure and group replacement at predetermined intervals. Consider 1,000 identical fluorescent bulbs. Individual replacement costs Rs 150 due to labor and disruption. Group replacement during planned shutdown costs only Rs 40 per bulb. The high individual cost reflects specific labor allocation, administrative overhead, and operational disruption. Based on historical data, we can establish the probability of bulb failure during each week of operational life. Week 1, 10%, Week 2, 20%, Week 3, 30%, Week 4, 25%, Week 5, 15%. To find the optimal policy, we must calculate expected failures per week, accounting for both original population and replacement population failures. Week 1, failures equal initial population times probability. 1,000 times 0.10 equals 100 bulbs. Week 2 failures include original population failures plus Week 1 replacement failures. 1,000 times 0.20 plus 100 times 0.10 equals 210 bulbs. This pattern continues, with each week's failures including contributions from all previous replacement populations. For individual replacement policy, average life is 3.15 weeks, giving 317 failures per week at steady state. Cost: 317 times Rs 150 equals Rs 47, 550 per week. Group replacement every week costs Rs 40, 000. Every 2 weeks Rs 27, 500 average. Every 3 weeks Rs 28, 833. Every 4 weeks Rs 34, 412. The optimal policy is group replacement every 2 weeks at Rs 27, 500 average weekly cost, significantly lower than individual replacement. Service level quantifies the probability of satisfying demand for a spare part from existing inventory at the time of request. A 95% service level for a critical motor bearing means 95% probability the bearing will be in stock when required and 5% probability of stockout. It is a direct measure of inventory availability and performance. Determining optimal service level represents a critical economic equilibrium between carrying inventory costs and stockout costs. Carrying costs include capital opportunity cost, warehousing expenses, insurance, and risk of obsolescence. Stockout costs include lost production, idle labor, emergency procurement premiums, and customer goodwill damage. This requires criticality analysis, such as ABC classification. Class A critical spares may require 99% service levels as operational insurance. For highly critical spares where stockout could precipitate complete plant shutdown, management accepts higher inventory cost. For less critical non-production halting spares, lower service levels like 90% may be more economically justifiable. Let's apply these concepts. As maintenance manager for a bottling plant, consider the main drive motor for the primary conveyor belt. Failure would result in complete cessation of operations. This requires predictive maintenance with continuous monitoring. Compare this to fluorescent fixtures in the administrative building. Perfect candidates for breakdown maintenance. HVAC air filters with known 3-month clogging patterns are ideal for preventive maintenance scheduling. For the main gearbox with complex, non-age-related failure modes, Reliability-centered maintenance provides the systematic approach needed. RCM's 7-question methodology determines the optimal mix of maintenance strategies for each failure mode. Modern maintenance management integrates all these approaches based on asset criticality, failure patterns, and economic analysis. Industry 4.0 technologies are revolutionizing maintenance through IoT sensors, artificial intelligence, and predictive analytics. Machine learning algorithms can now predict failures weeks in advance, optimizing maintenance timing and resource allocation. Augmented reality guides technicians through complex procedures, while digital twins simulate maintenance scenarios. Effective maintenance policy transforms from reactive cost center to strategic competitive advantage. Success is measured through overall equipment effectiveness, cost optimization, quality assurance, and safety performance. The journey from fixing what breaks to preventing what might break requires strategic thinking, proper tools, and organizational commitment. Master these principles, and you'll transform maintenance from necessary expense to strategic asset, the foundation of operational excellence.